One. Okay, last lesson on Friday was independent events. So the opposite of that is dependent events, which are events for which the occurrence of one does affect the occurrence of another. The formula for calculating it looks the same, but the way that we write it, the way that we express the formula is subtly different because you have to consider whether an event occurred or not. So if A and B are dependent events, then the probability of A and B happening is equal to the probability of A times by the probability of B, given that A has occurred. You have to say that because A has an effect on B happening. So get that example down. A fruit bowl, 3 apples and 5 oranges. Callan selects a piece of fruit at random and eats it. His sister Michelle then selects a piece of fruit for herself. And we want to find the probability both pieces of fruit are apples. And B, the probability that Callan selects an orange, Michelle selects an apple. Got the example down, we'll talk about it. You lose my John Z? You swear in my YouTube video?
Sorry about that.
We used to be cool. Now it's just... I'm rethinking this whole relationship. What is the thinking? Are these events dependent? Can someone explain why they are dependent? There's one statement that you would say that explains why they're dependent compared to our example before with like the coin and the dice, yeah?
Because when the first Callan picks a piece of fruit, it changes the outcome and the probability.
Yeah, that's an Ignite answer. You could just say it gets eaten, yeah? Right? That's the difference. He doesn't put it back, he gets eaten, yeah? Why it gets eaten, therefore the sample space changes for the second one. So probability of A and B. So how do we answer A? Probability of, apple, then apple. What's the probability of Callan getting the apple? How many pieces of fruit are there in the fruit bowl to start off with? 8. And what's his chances of getting apple? 3. That's his chances of it. But then Michelle, he's eaten an apple with the 3 over 8. How many pieces of fruit are there going to be after that? See how the sample space has changed? It's over 7. What's the chance of her getting an apple? 2, because one's been eaten. Multiply the tops, 6 over 7 by 8. What's that, 56? That's one of the ones that I have to check. I don't know. 56. Yeah, 56. That's divisible by 2, 3, 25, 26, 27, 28. Does 3 go into 28? No. B. Find the probability that Callan selects an orange and Michelle selects an apple. So probability orange, then apple. What's his chances of getting an orange at the start? Times by. 1 gets eaten, so it's going to be over 7, but now 3. Good. 5 times 3, 15 over 56. Does 3's go into 56? 1. No. Just leave it at that. Okay. Next example is 1. Oh, sorry, I'll give you time to get that, please. Next example is Curly's favourite, tree diagrams. Look at it. The face. The knee.
Would you be friends with me? Like my eyes just go upwards and then you can put down. What? What do you mean? Like you know how eyes are like that?
But not everyone's eyes are like that.
You're saying your eyes were like that? No, like that.
What was the question?
I wasn't here on Friday.
So independent was like if I rolled a dice and I flipped a coin.
Yeah.
That dice isn't going to affect the sample space at this point. Whereas here, because it's getting eaten, it's being consumed. These would be independent if he picked up the apple and put it back. Because it's consumed, it changes everything. All right, let's have a look at the tree diagram. Shh. There's a lot of chat. There was only a couple of tree diagram questions in the test. I'm the troll of trolls. We can do like a 20-sided dice. What happens if I roll the 20-sided dice 3 times? Draw a tree diagram on this A1 piece of paper. We could arrange that. So, hey, I wrote them all. A container holds 3 banana ice blocks, 4 chocolate ones, 2 raspberry blocks. George randomly selects an ice block from the container and eats it. So that confirms that it's going to be dependent. His brother Oliver then randomly selects an ice block from a container. Draw a tree diagram to display the possible outcomes. How many sets of branches are there going to be? How many levels should there be here?
3.
How many selections are there going to be made? How many people are choosing? Just 2. There's going to be 2 levels of branches. You're thinking about the actual branches, okay? So there'll be who was first, George, and the other was Oliver. Now we go with that number, because that's right. How many colours does he have to choose from? George? 3. Banana, chocolate, raspberry. Then after George has done that, banana, chocolate, raspberry, banana, chocolate, raspberry. However, this is not going to be as simple as what we did on Friday because all those probabilities change depending on what branch you go down. Let's look at George. I'm missing one. Let's go out there. Banana, chocolate, raspberry. What is the chance of George selecting the banana? What's the sample space at the start? Yeah, but then someone's cancelling down. 3 over, 9? 4, 5, 6, 7, 8, 9? 3 over 9, 1 over 3. I'm just going to keep it as 9, so I don't do any, I'll cancel right at the end, okay? It's just easier for me to see the sample spaces when it's like I don't cancel it there. Chances of chocolate, 4 over 9. Chances of raspberry, 2 over 9. Now you have to think, because the numbers here are going to change depending on what branch they went down. They're all going to be over 8. Do you agree? All over 8, so fill that in. Over 8, over 8, over 8, over 8. But if George selected a banana, how many bananas will be left? 2. If George selected a banana, how many chocolates are going to be left? 4. Didn't get affected. And 2 raspberry. See the thinking behind that? You have to trace through. You can't just copy the numbers down. We need to go through that middle tree that's now going to be on YouTube forever. 4 over 9. Banana. That didn't get affected, did it? 3 over 8. What about banana and... No. Chocolate and chocolate. It's going to be 3 over 8. Does that make sense? And then 2 over 8. Can you please notice as well? You can check you're doing it right because these should add up to 1. Because the full chance of something happening, 2 plus 4 plus 2, that should be over 8 in total. And then last one, raspberry... banana, same, chocolate, same. 1 raspberry, because he consumed 1. Find the probability that the brothers select the same type of ice block. Are there multiple branches here that represent them getting the same ice block? How many? How many? 3. George, banana. Ollie, banana. They got the same. Chocolate and raspberry. So now I need to move this one. I don't give enough space for that. Probability both same. We're going to do some timesing and adding. So the top branch is going to be 3 over 9 times by 2 over 8. That's the first opportunity to get two of the same. Then we need to add, what's the two numbers I'm going to times together for chocolate and chocolate? 4 over 9 and 3 over 8. Last one, 2 over 9 times 1 over 8. Top by the top, 6 over, is that 72? I think so. 4 times 3, 12 over 72. 9 times 8? Get the calculator to check. He's meant to be a maths teacher. Geez, 72 years. Right? And then plus 2 over 72. Are they all the same denominator? So I can add them together. 18, 19, 20 over 72. 10 over 35, 36. Still divisible by 2, 5 over 18. I think you can leave it at that. 5 over 18 chance that they get two of the same ice blocks. That's how that works. I'll stop the video there.